Good morning, everyone. I am Astha Parashar.
And I am Anisha Khose. Welcome you all in the behalf of IPS Academy Institute of Engineering and Science. Welcome to day 2 of our discussion on special day event Faculty Development Program on Design and Simulation of Next Generation Semiconductor Device and its application for biosensing. As we move forward in today's session, we have among us our chief guest, Dr. Vikas Vijayvargiya sir.
Sir has completed his M.Tech in Microelectronics and VLSI Designs from SGS-ITS Indore in 2009. He has completed his PhD in Department of Electric Engineering from IIT Indore in 2016. His area of researches including the designs, modeling and analyzing of advanced MOSFET devices and its circuit applications for low power applications. Sir is currently working as Associate Professor of VIT Vellore, Tamil Nadu in India.
To express our profound gratitude, I would like to invite Dr. Nitin Jain sir to felicitate our chief guest Dr. Vikas Vijayvargiya sir with sampling gesture symbolizing our gratitude for his presence and wisdom. Now I request Dr. Vikas Vijayvargiya sir to uphold the dice. Welcome sir.
Very good morning. So this is my privilege and this is my honor to invite in this AICTE training learning FDP faculty development program on design and simulation of next generation semiconductor devices and its application for the biosensing. I would like to present next generation electronics, and then also I would like to express my experience toward the nanotechnology's impact on a semiconductor device, circuit and system. So first we have to, system is nothing but it is a specialized hardware. Nowadays we are moving from the general purpose hardware to specialized hardware. And come to the next. So this specialized hardware mostly it is useful in a different number of sectors like that agriculture, automobile, healthcare. Okay, so in this specialized hardware, mostly the biggest challenge is the computation and power consumption. These are the two biggest challenges. So and also main important thing is that the system should be must be compact. And compact is totally depend upon to the hardware at the bottom what the hardware is there. So hardware is definitely at the traditional our transistor hardware transistor is the planar FET, and we are moving towards the nano sheet. So this FDP is totally based on the biosensing application and next generation electronics. So I will try to connect my presentation towards the biosensing application. Although my research area is not that, but from the last few days I am working on that, and I feel that that is the very upcoming domain, especially for the when we move for the AI aspect, and all the healthcare computation will do with the help of such data computation with the AI algorithm and specialized hardware if you place. So definitely it will be the very interesting domain, and we can come up with the number of research work for that. So toward this my presentation outlines are this. First I will discuss the next generation semiconductor devices and issues with respect to biosensor application. Okay, and then after I will discuss the device simulation and circuit design, and then I will also introduce if the MOSFETs nowadays challenging number of issues. So what should be the alternative transistor that will replace the MOSFET? So I will discuss in my third point, and finally that is the very, very important domain. It is neuromorphic circuit and system that will mimic the human brain, whatever the functionality and architecture. Accordingly, we will going to mimic the such system that will become under the neuromorphic circuit and system. I will cover in these things. Please come to next. So as I said, this is FDP mostly the dedicated for the biosensing application, next generation electronics. So first we have to understand what is the biosensor. Biosensor is nothing but it is a analytical device, and the analyte will interact with the bioreceptor. Analyte may be antigen, anything the live element. So it will interact with the bioreceptor, and it will, depending upon the analyte concentration biosensor, bioreceptor that is will be placed onto the sensor, it will interact with that and it will generate the biosignal. So depending upon changing on the concentration, like that glucose we place, depending upon glucose concentration will change, it will generate the some biosignals. So we have to measure such concentration through the electronically, and that is electronic important role is there. So electronic component will work on the electrical activity. So transducer is required. So then after such biosignals will convert with the help of transducer into the electrical signal. So here this is the functionality of the biosensor based system. After converting to the electrical signal, then electronic role will be come into the picture. Means the electrical signal, it is a very weak in that magnitude and strength. So we need to amplify, and weak signal will also merge with the some noises. So need to remove these noises. Some signal conditioning is required, and then after we have to amplify this signal. Amplification, and then after we should go for the processing aspect. Processing, maybe your DSP processor, your general purpose processor will be there, and finally we have to display the whatever the things we are going to measure. It will be, we need to display onto the measurement device. Okay, so electronic part will be there, and the system should be the compact. So compactness is totally depend upon your hardware. Yeah, this same thing it is mentioned here. Come to the next slide. Yeah, here you can see this portion, it is totally electronic. Although we can use transistor as if we are using the FET based transistor, so it will also come into the electronics. So mainly issue is that we have to take care as the research point of view. We have, as the research point of view, we have to understand what are the issues involved when we move from one technology node to the another technology node. So it is not a straightforward. So we have to observe at every technology node what are the issues are there, and so that we can integrate the electronic in a system. So my main intention to discuss upon this one, what are the issues are there and what is the next generation electronics. So we come to the next slide. Yeah, that is the main component of the biosensor. As I said, analyte, bioelement, that is we place onto the sensor, and transducer, that is the things. Come to next slide. Yeah. That is the one picture in which our main intention to discuss about this electronics part. Come to next. Yeah, and second one thing, as I said, nowadays our computation is going to change from the computer based computation towards the data computation based. Okay, so AI based processing is very, very important. With the minimal input, and will take the number of output. Like that, with the glucose, we can not only will check the glucose concentration with the help of glucose data. If our model inside this processing part, if you place the model like that, it will detect the number of things apart from the glucose concentration, like that the heart rate and other kidney failure, and if it will measure, that will be given by the AI. So now the system is like that, it happenings. So my purpose to discuss about this one. So main thing is the computation. Computation is the biggest issue, and if the parallel processing will be done, if the traditionally will do, it is not possible to come up with the compact device because power consumption will be there. And second one thing is that it is the totally if we go for the traditional, means if the computation will do with the non-Newman architecture based, means like that our traditional computer will have the processor and memory at the distant location, and we place the data at the memory side, and the computer your processor will fetch the data and then process and again send to the some display place. So it will take this some, it will cause the delay, and also this movement will take the power consumption also. So that is the problem. So as I say, that's why I said now the domain is totally changing, and we are moving towards the neuromorphic system, and so that the data analyzing will be very easy. Okay, so I will highlight at the end of the neuromorphic system how we can develop the AI accelerator. Okay, I will discuss. My few students are working with one my Finland friend, and they are working on the AI accelerator. So that experience I will share at the end. Okay, please come to next slide. Yeah, this is the one example I will explain the last time. Yeah, so as I said, these are the basic electronic components when we develop the biosensor based system. So transistor, signal conditioning circuitry, microcontroller, microprocessor, data acquisition system, display unit to control the display unit. So that is electronics also required. Memory is the biggest issue. 90% area is covered only by the memory. So that is also important parts. Means these are the electronics. So electronics is a great impact on the system, and we have, yeah, come to the next slide. Yeah, so it is necessary to understand the next generation semiconductor device and its issues to realize this such type of a system. Yeah, so for this I will discuss, all you know about the MOSFET. MOSFET is the fundamental device to realize such a system, and MOSFET is used for the amplification purpose. Also it will be used for the switching aspect. Yeah, come to next slide. So not only the biosensor system, many electronic systems are there that will it will define its efficiency, and also it will define its performance only with the help of MOSFET. Yeah. So now I come to the MOSFET point of view. What are the issues are there, and we have to handle these issues so that we can realize the biosensor system. So nowadays MOSFETs are aggressively scaled down and put the MOS device into the nanometer dimension. The main intention of the scaling is to increase the transistor density on the chip, and with this density definitely functionality will also enhance. Not only the increase the speed, because transistor will come very source and drain. MOSFET will in cross sectional issue will observe the source and drains, then it will become very close. So it will enhance the speed also, and apart from that analog and RF figure of merits also it will also improve. So come to the next slide, ma'am. These are the advantage. So whenever we any persons doing the research work for this biosensor based, so ultimately we are realizing the such a device on some ticket tool. Okay, so first purpose to whatever the device we are going to realize, we have to check its DC performance and its analog and RF figure of merits, whether it is suitable or not. We have to fix such should be in limiting value. If it is not in limiting value, the device will, when the sensor or any device will use for the circuit aspect or sensor aspect, so the device will be the leaky device, and it is not possible. So that's why ticket tool is there. So at the simulation level we can check all this aspect. So these are the DC parameter, means whatever the device we are using, if you are going to design it, on state current should be effective, and also off state current should should not be there. Means on by off ratio, it should maintain the on by off ratio. Okay, so practically 10 to the power 5 is the ratio between the on and off. And if the off current is going to degrade, so that off current to degrade means if we are not maintaining this ratio, it means the device is the leaky device. So all these things we have to maintain at the device level while we do the simulation. And one more important parameter, that is the subthreshold swing. And this parameter is very, very important for the biosensor aspect. Subthreshold swing means how the transistor is going to turn on and turn off, how effectively. With the small minimal voltage, how the transistor going to turn on, or with the minimal voltage we degrade, how it will turn off. So if we keep this swing minimum, so definitely the sensitivity of the transistor is good, and sensitivity is the biggest parameter for the biosensor. Okay, so that's why DC parameter calculation is required whenever we realize any device onto the any ticket tool. Apart from this one DC parameter, we have to check the AC parameters also. That is the transconductance. All you know, transconductance means how effect changing with respect to MOSFET, changing in the current with respect to change in gate voltage. And conductance, we have to check it, how it will be between the drain and source, how the current is flowing, and how much resistances will be there. Apart from this one more important parameter, that is the transconduction generation factor, TGF. Okay, so this will also transconduction generation factor means that it will indicate with the minimum amount of power how much your sensor is effective, how much it is converting to the changing the current. If you are changing any bio signals, or if you are measuring any bio element through the transistors, so little bit change in dielectric or charge, if the current is changing, it means it is very effective. with the minimal of the power. So that capability will be checked with the help of TGF. Okay. Another parameter, that is we have to check the capability for the device up to what frequency it will work effectively, and then it will get down. So we have to check this one. So when the purpose is that to discuss this one, whenever we go for the realize any device for the biosensor aspect or for the circuit designing, we have to check these parameters, DC, analog and RF figure of merits. We have to check it. Okay. Yeah. Please come to next slide. I will discuss. Actually, I am not able to access the ticket tool from my. Otherwise, I will explain here through the how we can do the simulation and we can calculate these parameters. Although I will just at the end I will explain the what are the tools are useful and how we can calculate these parameters. Okay. So apart from these advantages, as I mentioned, these are the advantage for the scaling. So two biggest challenge is scaling is not a straightforward. When we move from the one technology node to the another technology node, we have to face the two biggest challenge. That is the one is the short channel effects, and second one is the power consumption. So in the first part, I will discuss the short channel effects, and then after I will discuss the power consumption that will limit the MOSFET useful, and we are searching for the new candidate that will replace the MOSFET, although it is not possible right now, but it will suggest if we go for the ultra low power application, we have to go for the alternative of the MOSFET. Okay, so these are the, with respect to these two challenges, I am going to discuss the what are the transistors we are using in current scenario to overcome such short channel effects. Yeah, please come. Yeah, short channel effects is the main important. So first we have to understand. Yeah, please come here. Yeah. First we have to understand what do you mean by the short channel. Short channel means the channel length. If it is channel length means between the source and drain, the length. Okay, that is the gate length. If the channel length is going to comparable the depletion barrier at this around the source and drain side, if it is going to comparable, so we can consider the device is a short channel device. So if it is there, so non-ideal effects will be there. So whatever the model we will place, like that, these are the long channel device current model. Okay, why we use this model? If we place this model, we can use this model for the circuit designing. That if it is compact model, we can go for the circuit design, and it is very effectively and efficiently we can check the circuit simulation. That's why ticket is very, very important. Why we go for the ticket designing. Okay, so we realize this model, and this model is for the long channel. Long channel means in micrometer, this length is there. So first we have to understand how we can understand my device's short channel. So the channel length is if it is going to comparable with respect to barrier between the source side and drain side, depletion barrier. If it is this depletion barrier width is going to comparable with the channel length, so we will call such a device as a short channel device. And if the short channel is there, definitely it will create some leakage issues. So we need to control, we have to introduce such device that will control such leakage. Come to next slide. Yeah, you can see here that is the long channel behavior of the character. So whatever the model I mentioned, that is a long channel. So what you observe, the current generally in saturation region, the current is proportional to the skew of the gate voltage, as you observe. So it will follow the skew law. But as we move from one technology to another technology, if the device is short channel, so other non-ideal effects will be there, and that we consider short channel effects, and your skew law will not follow. It will go, you are observing here in the spacing between the one gate voltage to another gate voltage in output. Yeah, please. Output, it is only linear behavior. Spacing is equal. Here spacing will follow the skew law. Okay, so that because ultimately we have to go for the physical device and physical system that contains the electronics, that contains your circuitry. Okay, so circuit should work perfectly whatever you are doing the simulation. So for the simulation, the model should be perfect. How we can understand model is perfect? We have to observe all such non-ideality at one particular technology node, and we need to incorporate such non-ideality in our current model, current mathematical model. Okay, then if it is okay, if we calibrate with the fabrication, if we go for the fabrication of the device, NMOS or PMOS device, if it is working accordingly, then we can say that my model is correct, and then that model we can use for the circuit simulation. Okay, Yeah, come next slide. So I will not go in detail about this, what is the short channel effects. So these are the short channel effects. Many more short channel effects are there, and this model we need to include inside the our model. Okay, then we go for the circuit simulation, or if you are going for the biosensing application, so short channel effect means the sensor, nowadays everything is a sensor based. Okay, so first interaction, the electronic system is the sensor only. So if the sensor will suffer with the short channel effects, so definitely it will be the leaky. Okay, so we have to place such a device that will overcome such short channel effects. Okay, so we have to understand what doing the short channel. That is my intention. Yeah. In a short channel effects, generally we can measure the one more important issue of the short channel effect, that is the DIBL, drain induced barrier lowering. That is a very, very important part. As the source and channel will come very close, we are expecting that gate voltage will control the channel. For if the gate is, we apply the gate voltage, the current should flow between the source and drain. If you are not applying the gate voltage, the device must be in off state. But in today's domain, it is not happening. So drain is become very close. So drain electric field also encounter into the source side. We apply some drain positive potential for the N channel MOSFET. It will encounter toward the source side, and it will degrade the barrier between the source and channel. That will block the current flow. So now the drain is also going to control. So that is the problematic. So what happened if you use the because in when we do the simulation, when you use the realize circuitry, we vary the power supply. We vary the drain to source voltage. At the 0.1 voltage, very less electric field at the drain side, source side, and at the 1 volt, at the same drain 1 volt, this electric field is more over there. So your threshold voltage is changing. Once you fix the device, the threshold voltage should not change. If it is happening with respect to changing in the drain to source voltage, if you are varying the drain to source voltage, threshold voltage is changing, it means your system, whatever circuit you will design with the help of this device, the circuitry will not be the stable. It will leaky device. Okay, so we cannot expect the required performance. So we have to overcome such short channel effects, and it should be in our limiting range. Okay, so we'll come to the next slide. So we measure this short channel effect with the help of this lambda. You are observing in this, if we increase at the low voltage, threshold voltage is up to here. As we increase the drain to source voltage, my threshold voltage is changing. It should not change. Once we fix the technology, if it is changing the threshold voltage with the terminal voltage when you apply, so it means the device is the leaky device, because the reason behind is that DIBL effect is there, and your device should be like that. It should reduce such effect, so that the changing in the threshold voltage will be acceptable for us. Okay, so short channel effect is the scaling, limiting scaling into the sub-nanometer dimension range. Come next slide. Yeah, so there are two ways we can, I'm just discussing general way. There are two ways we can control the short channel effects: device engineering and using the multi-gate architecture. Okay, although all multi-gate architecture also will come under the device engineering, but I divide into two parts how we can control the short channel effects. So in device engineering, come to the next slide. Rather than we can, that is the one way we can do the improve the short channel effects. That is happening at the more than 65 nanometer. So we can some researchers have introduced the rather than uniform doping in a channel, they introduce the lateral asymmetric in doping. Means doping is not constant, uniform. They keep asymmetric doping in the channel. So they observe that the device is the less short channel effects. The short channel effects will be in the under the control range, and then we can use for the circuit aspect. Other aspect is this source and extension. Along with, we can use the spacer for that. Also, we can replace the gate oxide low K to the high K. Although we have to also check it the whether we are using whatever the dielectric, it is feasible or not. Okay, although at the simulation level we can do anything, but it should be feasible. So what happened is, as we scale down the device, so supply voltage we should also scale down. Okay, and another way is that with the increasing the gate voltage or scaling of the gate voltage and scaling of the device, this physical dimension is also going to reduce. So what happened? This gate oxide thickness will also reduce. So the electric field, vertical electric field also is going to increase. So if the charge carriers are moving from the source to drain, because of this gate voltage is positive or depending upon the what type of channel you are using, it will tunnel through the gate oxide and reach to the gate side. So the leakage, so that will also come under the short channel effect, gate tunneling. Okay, so is depending upon what technology you are working, what are the issues are there, how you can handle these issues. Like that, this type of high-K dielectric is introduced at the gate oxide. Generally, SiO2 we can use, but at this after 65 nanometer technology, we start using the high-K dielectric to reduce such. If you increase the dielectric width or dielectric constant, if you increase, so definitely the leakage will reduce. Okay, so after that it will start. Yeah, come to the next slide. So these are the device engineering. Okay, so yeah, come to the next slide. Earlier I discussed some device engineering, that is the doping based, channel doping based, or some by changing the gate oxide, that will be useful to for improving the short channel effects. Another, as I mentioned earlier, that drain electric field it is encountered toward the source side because the source and drain is very close. So this effect we can calculate with the help of Dibble, and another parameter that is called the lambda. Lambda is the electrostatic integrity factor. It measures how much drain electric field encountered toward the source side. If its value is less, it means the device is very effective. We want to reduce this value. It measures this capability. So how, that will give some analogy how we can improve such electric field from the drain side. It will come to the source side. We have to block. Our device should be turned on and off only because of the gate voltage. But if it is happening because with the gate voltage is low off, if it is happening because of the drain, it means the device is not suitable for you. Okay, so you can see here this electric field is reaching here at the source side. That is our planar device. Now if we introduce any gate, so it will be blocked here. The electric field that is coming inside, it will be blocked. Okay, so that's why multi-gate architecture come into the picture. Okay, come to the next slide. Yeah, that is the double gate FinFET. There are two-way orientation. If you place like that is a double gate, and if you do like that is a double gate FinFET. Okay, so gate volt here oxide thickness. Yeah, so here you are observing that gate oxide thickness is we can keep very large in length. Okay, in the width. So there is no effect of gate. This one is the double gate. This red color is in gate. Okay, so this electrode is integrity factor we can calculate with the help of this. That is the modeling. Some researchers have do the modeling because lambda. As I said, lambda it should be minimum. It should be minimum. Okay, it indicates that if its value is less, means less drain electric field is reaching towards the source side, and the device is not leaky. Okay, so this with the help of this lambda we can do it. So this technology, this architecture, this multi-gate architecture will again continue the scaling of the device, and after 22 nanometer this double gate SOI based will be useful for that. Now you can see here is again if we continue scaling, we reach to the 14 nanometer or below 20 nanometer. Again it observed that the device again become the leaky device. It means whenever the device is going to leaky device, it means gate is losing its control onto the channel. Gate is losing its control. Its channel means other terminal device is going to affect in the device. So device is the leaky device. So how we can control this one? Earlier we control with the help of introducing one gate. If we introduce another gate, you can see here that is with respect to this device, here oxide thickness is large, but here oxide thickness is very small. Okay, it means it will this upper gate is also, if you apply the voltage, upper gate is also effective inside the channel. It means it will become the triple gate. Okay, so triple gate also improve your electrostatic, means it will also increase the control ability on the channel. So this again it will continue, that is a triple gate FinFET. Okay, tri-gate we can call it. So you are observing with the help of this electrostatic integrity factor lambda 3. With respect to this one, you are observing here the one parameter. Yep, one parameter is there, one value is there, that is divided by 2. Here the everything is same, only the 3 is there. It means the value is going to reduce. It means the device means when the my purpose is that whenever we use the device for any application, for the biosensing application or for the circuit application, first we have to confirm my device should not be leaky device. If it is leaky device, it means some short channel effect is there. You have to introduce such device, such transistor. You have to come up with some idea that will reduce such short channel effects. Like that, someone have researchers introduced the tri-gate. This FinFET technology is heavily used. and it will continue up to the 5 nanometers we are using. Okay, so main problem is that the current driving capability, although definitely for the this type of technology, throughout the gate we are going to at the 3-side gate, it is going to deplete your channel. It means whole entire region of the channel is going to deplete, and we can use for the conduction aspect. Okay, so but the silicon thickness it is going to reduce. So to increase this current capability, we will go for the multi-fin. That is called the fin. Like that is in window, number of rods are there, that is like a fin. If we increase number of between the source and drain, if we increase we introduce many more such rods, many more such fins, so we can increase the driving capability of the device. Okay, so driving capability is a very, very important part for your circuit designing or for the biosensing applications. Okay, then we can after the 3 nanometer, not 3 nanometer, after 5 nanometer, again FinFET technology is not suitable. The reason behind it is that if you go below 5 nanometer, the fin aspect ratio, width and length, width and height, the ratio also creating the problem. We cannot, that is a scaling limitation. And also the pitch from one fin to another fin, the distance we are not able to scale down. So again, after 5 nanometer, means when we go for the next, after 5 nanometer, when we go for the next advanced node, again the problem started, that is the controllability of the gate. Okay, so what is happening? Double gate solve the problem at the 22 nanometer, and we come to the 14 nanometer. Again leakage started. Again we go use the help of tri-gate. Again introduce another gate. Again it will start continue the scaling, and then we come to the 3 nanometer. Again 5 nanometer. Again we are facing the problem of the leakage, because we have to maintain the on by off ratio. If current is good, definitely current is good, on current is good, but simultaneously off is same, that is the same amount. Okay, that is not a useful device. If the device is ideal in a circuitry, it will consume, it will drain the power from the power supply. It means our system will not retain battery backup for the long time. So this is the big challenge for this one. So we have to, that is the problem, and we measure this whenever we write the device or develop the device, or we can introduce any idea. So it should, the short channel effect should be in a minimal range. Actually, I am not going to discuss all the short channel effects, but whenever you do the such device based some research, so first you have to check it the all short channel effects, and then you have to come up with the new device. Not only the multi-gate architecture, in multi-gate architecture we introduce some spacers, high K spacers, low K spacers, dual K spacer. Not only the spacer gate we can divide in the two parts. At the source side we can put the low K gate oxide, and at the drain side in the channel region we can put the high K. Rather than single gate oxide, we can go for the dual metal gate, dual oxide, or we can go for the dual metal gate. So these are the different way we can control the short channel effects. And it should be, actually I am not putting some measured value here. What is the dibble? Dibble, I think it should become 60 millivolt per volt. Like that, if it is less than, the device is the leaky device. So whenever we can go for the designing any device, the device should be, will have some measurable values. Okay, if it is measurable value is in our limiting range, then with the devices we can use for the circuit aspect. Okay, you are observing in the last slide gate around structure. Yes, in this gate around structure, here you are observing that the divide by 4. It means electrostatic integrity factor is also improved. If its value is minimum, it means the device is more suitable for the means it will improve the short channel effect. It is not a leaky device. Okay, so nowadays we are using such device. 3 nanometer, I think IBM has some introduced, and they are working on this one. They come up with some production also. Yeah, come to the next slide. These are the advantage. These are the same thing. These are the advantage. Volume inversion. Volume inversion means entire channel we can, because entire side gate is there. In channel entirely it will deplete. So we can entire channel we can use for the conduction aspect. Okay. Second one thing is that if we increase the number of gates, lambda will improve. Okay. So whenever we devise, actually that is not a correct relation, but some researcher suggested that whenever you going to introduce any device, at particular technology length, the length should be greater than or equal to 3 lambda. That is if this mathematical relationship established, it means you can continue for the other calculation. If it is not there, definitely the device will be the leaky device. Okay, na? Yeah, come next slide. So multi-gate MOSFET have shown its potential to minimize the short channel effects. In this entire thing, not only the multi-gate, as I said, we can use the spacers also to add particular technology node. If we want some trade-off will be there, because we are using the drain and source extension. So if we are using the extension region, it will introduce the resistance. So to overcome such a resistance, we can use the high K spacer rather than low K spacer. Always extension region will use the spacers. So spacers means at the extension length we put the some dielectric, other dielectric. Okay, so high K dielectric we use at the spacers, it will reduce the resistance but increase the capacitance. So again, it will make our device make a performance will be the issue, but it will improve your short channel effects. It will improve your, it will increase your current capability. So there is a trade-off between this one. So we have to maintain the trade-off also. Yeah, come to next slide. So all you know about the Moore's law. So ultimately, everything is happening towards the Moore's law, and researchers are suggesting that Moore's law is going to end. And second one thing is that Denott's density rule also there. So if both will combine, that will Moore's law will tell to make your chip more powerful. Means we are placing more and more transistor on the chip. Dennard density suggests that if you keep increasing the transistors, you have to scale down the supply voltage also. But supply voltage we cannot scale down like that. We are geometrically scale down the transistors. Okay, so that will limit. It suggests that power density should be constant if you are increasing the number of transistors. So it maintain the scaling of the supply voltage is not a linear manner. That is the biggest challenge. Okay, come to next slide. So this one is the, as I said, the FinFET is the limitation. Up to the 5 nanometer, FinFET is going to use. Okay, the limitation in count that the fin pitch we cannot scale down, and this aspect ratio, height upon width, that ratio, height upon thickness, that ratio is also going to be limiting. Okay, so that will create the problem for the limit. Okay, so that's if you use below 3 nanometer, again the control ability will be the issue. Control ability of the gate onto the channel, it also become the issue, and it will create the leakage problem. Okay, so that's why you come to the next slide, man. That's why we are moving from the, that is the FinFET, three side it is the gate. Now that is the current technology we are using. And someone have number of research papers are there that come up with the biosensor for the nanosheet based biosensor, nanosheet. Okay, here you are observing my channel is vertical, the sheet is vertical. Now it will become the parallel. So in the same footprint area, we can place number of channels are there. Okay, that is the current technology, and IBM or other companies are using this for the 3 nanometer device. That is the nanosheet. Okay, and it will control, and I think that will continue up to the 2 nanometer also. Although we are reaching towards the atomic range. So scaling is not a biggest challenge. When challenge is the power consumption. If you are increasing number of transistors on a same chip, how you can handle the power? All power consumption, because number of transistors will work over there. Billions of transistors we are. It is not a VLSI. That is the ultra VLSI technology. We are reached towards the ultra VLSI. ULSI. Okay, so power consumption is the big issue, and nowadays most of the now I'm also doing the work for the this nanosheet aspect along with my friend that he from the Germany. He is good in modeling. So we are doing the model for the thermal effect, temperature effect on the nanosheet, and we are developing the model for that. Soon we are going to publish this paper, but number of researchers are working in this aspect. So if you go through the literature of this one, if you are interested in these things, definitely in a limited time you come up with the good results and come up with the publications. Yeah, come to this next slide. Yeah, here you can see that is the last slide. Yeah, this is the picture what I discussed. Up to the here you can see planar FET up to this 14 nanometer at 22 nanometer. that is a planar FET. Okay, then planar means that is your source and drain. It is a plane like that. When it will come, your source, your channel will come in the 3D direction. So it will become the source. Your channel will come up from the substrate. So it means it will become the 3D. Okay, although device is 3D only, but like that we can consider. So here you can see up to the 7 nanometer, that is the FinFET. It is up to the 5 nanometer we are using. You can see that is a picture 5. Now below 5 nanometer, we are going for the nano wire. Nano sheet is the one type of architect. Nano sheet is that will come gate around. Nano sheet is also gate around, but the current flowing in the sheet format, and sheet is in horizontal like that. Okay, so with respect to FinFET, in the same footprint area, we can introduce number of sheets, and we can we can increase the current driving capability, and it also support for the for scaling of the device. Why the scaling? Because it will improve the short channel effect. Our gate is surrounding the channel. Okay, so now below 3 nanometer, these are the proposed device, and I think it will continue up to the 2030. We can go for this one. In the same manner, ICs also are going to be developed. We are going towards the monolithic IC, that is the heterogeneous IC. Recently, there is a one talk with the VLSI Society in our VIT campus. So they suggested, please start the work. You suggest your student, you suggest your faculty do work for the heterogeneous aspect. Heterogeneous means not only silicon material. You go for the means one IC not only dedicate not only one circuitry. Different type of circuitries will be there, and it is in the form of like a flat system on chip and system in package. This is the two things. System on chip means definitely one floor is there and we place one building, one floor we place. But the problem increases because we are keep increasing the density, and we want to continue the Moore's law. We want to continue according to the Dehner density rule. Okay, we have the researchers are going to introduce the monolithic IC, means like a flat system. Means each layer will dedicate, each IC layer will, IC means number of ICs we are integrating in a single IC. That is called the package. And our smartwatch and this ones are only possible only because of this reason. Okay, so number of packages are there. Apple IC, as I mentioned in the one slide, one figure I said I will discuss in later on. That is Apple IC, that Apple watch, in which they use the package only. Okay, so definitely up to the 2035. Recently they published the roadmap for the semiconductor technology. What will be happen in next? Because the main problem is the some persons are telling that Moore's law is going to end, and some is suggesting that we are going for the beyond the MOSFET. Some are suggesting more than Moore. How it is possible? Moore is going to end. We are going for the more than Moore. That is the biggest discussion among the researchers and industries aspect. Okay, so definitely it will be continue with this such type of transistors. Yeah, same thing I mentioned here. Same picture I mentioned. I said here up to the 14 nanometer. That is your 30 to 42 nanometer. That is the high K base or planar type of device. Below, although it is 22 nanometer only, 42 nanometer, 3 nanometer FinFET in different shape it is coming on. It comes from the first generation, second generation, third generation, but that is a tri-gate only. Then after nano sheet, that will come 3 nanometer, below 3 nanometer it is there, and these are the possible structures are there. Please come. That is the current scenario we are using for the not only the circuit designing, for the biosensing aspect we are using this one. So that sensor system will be integrated in a system. Okay, so in a sensor, not only sensing, we have the rest of the electronic parts is also there. Okay, so these are the roadmap that is proposed by the this IMIC. So this will give very interesting thing. Actually, what is happening nowadays? Main problem is that edge computing is it's happening surrounding us. Edge computing means the system is required. You are at the local site, means at local server side, everything will compute rather than it will go to the cloud. Okay, so for that purpose, nowadays we are going for the 5G. The advantage network is also going for the high speed. So our system is totally data based. Data manipulation, as in starting I said, computer computation rather than we are going for the data computations. Okay. and to bring the data from the server. Earlier, what the issue is that the data is available in the server and bring at the your client side, and again it will compute and again send it. So it will take time. The reason is that earlier the bandwidth is not available for the internet speed is not like that. Okay, so now it will possible when we'll go for the 5G to 6G or 5G, that is possible. High speed internet network is there. So all these things are possible because it is possible only because of this VLSI. With this edge computing, that is related with the IoT base and data center and high speed networks, that will enable the VLSI, that will make our VLSI chip more powerful, and all these things happening on the semiconductor technologies. So you are observing that I will give the conclusion for this one. In 20 years, the integration density system, I mean semiconductor content in electronic system is going to double. And with the help of this AI computation, it is also definitely this trend will continue, and you can think about what the next shape will be in the market. Okay, please come next slide. So this I suggested for the biosensor, for the circuit designing, what should be the next semiconductor device, and we can continue our research this aspect also. Now little bit I will discuss about the device simulation and circuit design. Recently we published one paper in Journal of Electronics Material that is only nanosheet based. So this will suggest how we can do the simulation. Not I will go in detail, only just I will tell you what I did, and we can also work in the same direction. And I will suggest some ticket tool also. Okay, please come here. We work on to the SOI nanowire FET. Okay, this FET, 3 stacks we use. Come to next slide. These 3 stacks we use. You can stacks. This is one stack, means 3 fins we have used. But surrounding we are putting the gate. You can see the color. Surrounding gates are there. Okay, come to the next slide. My main intention here to check this capability. That is the source extension and the drain extension. So we place the because every source extension or drain extension, it required the spacer. So we check the capability if the spacers will change, spacer length will change, or this drain extension length will increase or decrease, or we can keep the symmetric. Right now this is a symmetric. If you go for the asymmetric, how it will affect the performance. But we have to come up with some physical outcome, why it is happening and why the performance are increasing or decreasing or degrading, why. Okay, so in that manner we have to come up with some simulation. Yeah, come to next slide. Yeah, that is the asymmetric. Here you can see here drain side I keep the symmetric length. Symmetric means source length and drain length both are same, but here you are observing source and drain length both are not symmetric. Okay, so come to next slide. For that we use the different type of spacers. So these are my device parameters I use, and I start the work. Yeah, please come. Okay, now I come to the tool. I will do this, continue this one. First I will, these are the 3 tools are there. Our VIT have these 2 tools, Silvaco and Centaurus. Although this work we did on a Cogenda Visual, that is a ticket. I suggest you, if you are interested in the work, go for this tool. It's a very cheap. Means we can go purchasing this license with a low cost. Okay, and have mostly, and the tool behavior is very simple. In one shot you can understand how we can go for the such next generation semiconductor devices. Like that I designed the nanowire. So we did the work, some collaborative work. One faculty joined over there, I collaborate with him, and they work on this one on Cogenda visual ticket. So we designed this nano sheet. So although Silvaco, during my PhD time I work on the Silvaco, and Centaurus still also there. So but it has in industry, most of the industry using the Centaurus for the ticket aspect. So this is the flow. I think most those who are working the VLSI, they know very well. That is the process based we can design. And at the device level, if you are start with the not with the, you are interested only for the device, you are not going for the process. Process means you will work at whatever the fabrication steps are there. When we send the design for the fabrication, what are the fabrication steps are there? Same fabrication step we can go at the simulation level. So for that purpose, we can go for the, in a Silvaco, there is one tool is there, that is the process simulation. Okay, will come under the Athena. Another tool is there. I start with this work on, because I'm not interested in the process. I want to work on device and want to check the device performance. So I start with the ATAL. ATAL is one tool, and over there is a we write some commands. That is the DAG build environment is there, and we can put it there. Okay, so I don't want to go in detail because that is a new thing for most of the here. I just suggesting how we can do the start the work. First we require the ticket tool. All tool will have the same flow. Only the nomenclature is different. But as per my experience, Silvaco, Synopsys, these are the standard tools, and companies, industries are there using for this is not Silvaco, Centaurus is using for their ticket work, means device level research. They are working using for the model development. They are using the Centaurus. But I suggest for the research aspect, it is low cost budget tool, that is the Cogenda. Okay, yeah, come to the next one. Yeah, that is the same thing. It is what I discussed. That is about the only Silvaco tool. What are the things are there? Once you do the device simulation, it will generate the log file that will contain the data, and you can plot onto the visual ticket, and it will generate the structure, that is the .str file. File format is important so that you can understand what things are you are going to do. Yeah, come next slide. Same thing it is there. These are the steps whenever we go for the designing at any tool. These are the steps. Structure specification, we start with the structure specification. Like that nowadays we are working for the 3 nanometer. First we have to study the literature, how we can realize the 3 nanometer, what type the source extension length, what is the drain extension, how to take the thickness and width. That we have to decide at the specification, and we start writing the things. Then we can according to the place the material model, and what type of method we are applying to calculate the electric field and all these things, so that we can go for the current calculation, all these things, and we do the result analysis. These are the steps are there. This is another tool. Why I'm mentioning here, because every tool have this some good feature. In come to the next slide, ma'am. In this Centaurus, that is the one platform it will provide that integrate all tools. Like that in Silvaco, device simulation you are doing somewhere, structure generating somewhere, okay, result you are checking somewhere. Okay, here it will integrate all the things at one place. That is the workbench. That is the interesting aspect for the Centaurus. All the things will be at the same place. Once you develop the device, you just generalize, you can just place the device dimension in a parametric base. You just select one particular parameter. Like parameter means in device channel length, oxide, or groping. These are the device parameter. Once you design the device, in terms of parameter, the parameter will reflect here. You just select one particular parameter, and you can start check the simulation. Here at the top level you can do this, and it will provide the result. So this is the interesting tool. So that's why most of the industries are using this one for their device aspect research. Yeah, completely. This is the flow. I don't want to discuss it. Okay. So one more suggestion. Yeah, why this one? I think some resolution issue. Resolution issue. Okay, I will explain orally. Okay, so I will share this PPT in the PDF format. You can do it. Okay, we come to the last slide. So whenever we do the simulation, first we have to calibrate our model, because at the simulation you can if you want to increase the current, you can do anything. You just change the parameter and you can go for the any current or any value, but it's not a correct, because if you submit your research paper, so the result should be authentic and it should be acceptable. So how you can go for such a simulation? So first step is that you have to calibrate your model with the measured data. Okay, model means these are the models, because we have to simulate your device. So the models we have to incorporate if you know the physics, the mobility model, recombination model. If we are working for the below 10 nanometer, quantum effect we have to include, so that model is there. So the tool will provide this model. So we have to include this model. But the problem is that this will contain the default parameters. If you use this default parameter based model, so it may or may not be accurate your result. First our step is that whenever you do the start simulation, first you calibrate your model with the measured data. For that purpose, you have to change the parameter of this such model. Mobility model will have some parameter, we change it and make the your current simulation, whatever the things are there, it should be calibrated with your measured data. Once it happens, then you start, it means your model is accurate, then you apply in your dedicated device, whatever the device. You can apply the model, you can check the circuit performance, device performance. So always researcher will ask, when we submit your research paper, so we'll ask what is the accuracy of your result. The accuracy we can suggest with the help of calibration of our model with the measured data. Sometimes we have to maintain the threshold voltage, sometimes we have to maintain the off current, sometimes we have to maintain the current, and then we can go for the simulation. In this, in the coming slide, I will suggest, I will discuss some MOSFET comparison with the tunnel FET. That is different device. So how we can compare these two devices? Okay, it is not a correct way we can just apply the same model. So at the time we have to maintain their off current both side. One parameter we can fix it, because tunnel FET will give the less off current, MOSFET will give the more off current. So that we cannot compare, because this is different conduction concept. Tunnel FET is different conduction. I will discuss this one. So first we have to go for the that is the space sensitive parameter in both the case. We can make it equal, and then we start the simulation. Okay, so calibration, that is my suggestion. Calibration is the important. If you are going for the sensing of, you are working on the biosensor or any device that is used for the circuit application, you have to first calibrate the device. So come to next slide. Actually, the main important parameter I want to show here, the subthreshold swing. As I mentioned, subthreshold swing is the one sensitive parameter. How effectively transistor can be turned on and turned off. Okay, so for the any biosensor designing, this parameter is very, very important. Okay, so if this value is less, it means your device is good. With a less amount of voltage, it is going to turn on. Come to next slide. Yeah, so this work I work, yeah, please come. Okay, so as in the starting I mentioned, we have to, whenever we start the working, we have to calculate the current DC parameter, AC parameters. Also we have to mention the AC parameters and RF parameters. So all these things we have to calculate, and we should confirm my device is suitable for the circuit aspect. Okay, come next slide. Yeah, one more interesting thing I am going to share here. Once we design the device and we want to go for the circuit capability of the device, without going for the compact model mathematics, because mathematical model developing is another biggest challenge. If you don't want to go for the mathematical model, you want to check your device circuit capability. So you just once you design the device and you confirm my device is less short channel effects, okay, then you can calculate the its capacitance, gate capacitance, drain capacitance, current with respect to variation of the drain to source voltage, variation of the gate to source voltage. These are the terminal voltage. With respect to this one, if you place all such values, you can accurately place in one table. That is called the LUT table, and that will give the behavior of this data. This data will give the behavior of your device, and this device you can call in circuit simulation. So here this is the picture. It is showing that once you do the device simulation, you can prepare one table with respect to gate voltage, current table and capacitance table, with respect to variation of the gate voltage, with respect to variation of the drain to source voltage. Because in a transistor, what it contains? It contains the drain to the terminal voltage and capacitance. If you prepare all such behavior in terms of some electrical voltages and capacitance, so that will make a table. And you can call this call in a one somewhere in a model. So that definitely we are calling NMOS or PMOS, whatever the table is there, and we can connect NMOS and PMOS in circuit fashion. We can check the performance. Yeah, this is the actually we use the, if you are interested to work in this aspect for the, if you design the device and you want to check the circuit capability of your device. So I will share this Verilog model for this one. This Verilog model will call this your lookup table. LUT table. LUT table, as I mentioned, that is the VDS and VGS variation with respect to what is the drain current. Okay, so but it should be very fine. In the same manner, capacitance, gate to drain capacitance with respect to this one. Okay, in the same manner, gate to source capacitance. If you table containing all this information, if this table will contain all the information, you can call this table using the Verilog model. That is LUT based model, and that is dedicated for your NMOS. In the same manner, you can prepare the PMOS. If you have the NMOS and PMOS, you can go to the Cadence or any EDA tool. You can just call it and connect NMOS and PMOS, and you can check the circuit performance. But the here condition is that we cannot change the channel length, because at one particular length we can prepare this table. In compact model, we can go for the mathematical model. We can do it, but it is a different type of research. We can do it. Okay, length we can change it, and we can do the simulation and we check it. But here, if you want to change the channel length or any parameter you want to change, you have to change the entire this table. But at one particular technology, whatever the parameter you fix it, you can check your circuit performance. For suppose you introduce one high K spacer, and you confirm that my device is good, it has the good on current, good off current, less short channel effects, having the good RF figure of merits, analog figure of merits, and you want to check some circuit performance, maybe your digital circuit or analog circuit. So you can just prepare this table, and with the help of this Verilog model, you call this LUT, and you can create the symbol on Cadence. Okay, although this simulation will be done in the Cadence tool. So NMOS and PMOS symbol we created, and we do the simulation. The picture is not visible. Here you can see this common source amplifier we design, and we check the, although as I mentioned in my device simulation, I check the spacer effect, symmetric and asymmetric spacer effects, and I want to check its circuit performance. So for the common source amplifier, and we calculate, here I calculated the gain, we check the who is giving the good gain, so that whether it is symmetric spacer or asymmetric spacer, so that it will be useful for the analog application point of view or for the sensing aspect. Okay, so that will give the circuit design. Okay, so I discussed these two things. Next one thing is that why we are moving for the, why we are searching the alternative of the MOSFET. Alternative of MOSFET means MOSFET will work on the thermal injection of charge carrier. That is the conduction concept, and it faces the short channel effects. And short channel effects we can improve with the help of multi-gate architecture or device engineering, as I discussed. But the biggest issue is that according to the Denode's density, we cannot scale down the supply voltage after 22 nanometer, as we are scaling down the geometric scaling of the transistors. Supply voltage is not a linear manner it is going to scale. We want to maintain the power density. If we increasing the transistors, we maintain the power density in a same area. Okay, so it means it is not possible for the ultra low power application. That is the biggest challenge. So it means why it is happening. So I will give this reason, and what is the possible transistors are there that can replace the MOSFET. MOSFET is work on the thermal injection of charge carrier. When you go through the literature, you will observe the conduction phenomena of the MOSFET. Current will flow from the source channel band to channel band. Electrons, after reducing the barrier, current will flow like that. Yeah, please come to the next slide. So up to this level, this is my second point. As I mentioned in the starting slide, short channel effects I discussed with respect to MOSFET. Now we come to the power consumption. Power consumption is the bigger issue. That will limit our device for the ultra low power application, because we are not scaling the supply voltage as accordingly as we are scaling down the transistors. Come next slide. So these are the different type of a device I discussed. Channel engineering, multi-gate architecture, the purpose to improve the short channel effects. And if you improve the short channel effects, it will allow for the scaling. If you not improve the short channel effects, your short channel effects is not coming to the control range, the device will be the leaky device. So that's why we are going for the different type of device engineering. So as I said, my second point is not the short channel, second point is the power consumption. Power consumption, there are two types of power consumption is there, dynamic power consumption and leakage power consumption. Leakage power consumption means if the device is static, means it is, your battery is going to drain, okay, so that is the leakage. It is not useful current, okay. That is the bigger issue in a MOSFET, and that's why we can keep we cannot scale down the supply voltage. If we scale down supply voltage, we have to scale down the threshold voltage also, because voltage is also there, so that to maintain the drive current at one particular technology load. Okay, so if we reducing the supply voltage, leakage will be the problem. Why the leakage is the problem in MOSFET technology? That will I give you the answer. Okay, Definitely with respect to scaling up the supply voltage, you are observing dynamic power consumption will reduce. It is proportional to square of VDD. That is going to support, but the problem is here, leakage. So these are the leakage current, leakage factors. These are the leakage factors. Okay, that is because of the short channel effects, in which subthreshold leakage current. Subthreshold leakage current is the big issue. Subthreshold leakage means because of the subthreshold swing limitation of the MOSFET. The subthreshold swing is the one parameter as mentioned in the starting. If you want to use the device for the digital application, subthreshold swing will suggest how effectively transistor turn on and turn off. If it is turn on and turn off rapidly, means device will be good for you. But as we scale down the transistor size, the subthreshold swing also we should scale down to maintain the leakage. You will observe the subthreshold swing, if it is not going to scale down, leakage will start increasing. Subthreshold swing, that will show the one slope. Okay, so this subthreshold leakage has become the problematic for scaling up the your MOSFET. There are number of factors are there. We can control other factors by changing the device architecture, by using the device engineering. But subthreshold leakage current we cannot control, because MOSFET will have the one limitation. Subthreshold swing, it is 60 millivolt per decade. We cannot go below this one. Subthreshold swing 60 millivolt per decade. It indicates that if you increase the voltage by 60 millivolt, your current will increase in one order. One order means like that 10 to the power 8 to 10 to the power 7 microampere, like that in today's technology in microampere. So to 10 to the power 3 ampere per micrometer we can use like that. Okay, so increasing order means from one decade to another decade, it requires at least 60 millivolt, and that is the swing. And that is the ideal, because of the MOSFET conduction will have such limitation. Yeah, I mentioned like that. Yeah, next slide. Yeah, you can read this leakage. This is an interesting paper. The Kaushik Rai it is given. You read all such leakage and clearly mention the subthreshold leakage is a very, very limiting factor to scale down the supply voltage. Yeah, mentioning here, I clearly mention below 1 volt it is very difficult to supply. It is not like that if you are scaling the geometrically scaling down the device, we are not scaling the supply voltage accordingly, but we have to scale down because we have to maintain the reliability. If you use the 2 volt very small type of transistor, definitely the reliability your transistor will burn out. So we have to scale down the transistor. We have to scale down the supply voltage. But the problem is that as per the Dehner density rule and as per the limitation of the MOSFET, leakage will start. To control the leakage, we have to scale down the subthreshold swing also. We should go below 60 millivolt per decade. But MOSFET, its conduction concept will have also its limitation. We cannot go below 60 millivolt per decade. Yeah, go to the next slide. So here, this is the MOSFET here I will give the answer why the 60 millivolt is the limitation factor. So this is the MOSFET energy band diagram. Okay, if you increase the gate voltage, this energy band will get down. The current will start from source channel to channel conduction band. Source conduction band to channel conduction band. The barrier will reduce, in which these are the capacitances are also involved. Oxide capacitance, depletion capacitance. Okay, come next slide. So current will flow like that from off to this on. If you keep increasing the gate voltage, current will increase. Okay, so this is your subthreshold swing, and it observes how it observes only it is 60 millivolt per decade. You can go next slide. Yeah, here this is the model, mathematical model. Someone have given this model. That is standard equation. Subthreshold swing means change in gate voltage, how the current is changing. Okay, so this equation is given by this one. If we maintain the ideal, if we remove the oxide, everything you remove, only the term will be left KT upon Q. Ideal case is not possible. Short channel effects will be there in some amount. We cannot make it short channel effects 0. If it is 0, means it's a wonder. Okay, we cannot do like that. So if you want to make consider ideal device, means capacitance effect will reduce. So your only the term will be left KT upon Q. Log 10 KT upon Q. KT upon Q, that is the 60. We'll multiply. You can calculate all these are constant. That is 60 millivolt per decade. It means subthreshold swing we cannot go below 60 millivolt per decade. That is the limiting factor. Means if the device achieve this swing 60 millivolt decade, you cannot go below this one. Come to the next slide, man. So what the problem observe, if you scale down the supply voltage, threshold voltage you need to also scale down, okay, to maintain the drive current at one particular technology node. You observe in the literature, you will think this like that, okay. But as you scale the supply voltage, because my swing is already 60 millivolt, my swing will be same. So my off current will be here. Off current I consider at the 0 voltage. My off current will be here. So to reduce this off current, we have to maintain this, sorry, previous slide, back, man. Yeah, we have to maintain this like that. Okay, so that is the main problem because of this. So the if you want to go for the ultra low power application, we should go for the alternative of the MOSFET. MOSFET, definitely we can improve the short channel effect, improve the leakage current up to some extent, up to the 60 millivolt per decade. Multi-gate architecture is useful. But if you go below this one, if you want to scale down supply voltage, it will create the limitation, and we have to search a new type of device, not only for the circuit aspect, for the biosensor and sensing application also. Okay, so alternative, yeah, you can see here that I have taken this picture from the Nature article. They create the revolution in the system, and we start working for the tunnel FET. Okay, tunnel FET is the device will not have such limitation. So this picture will suggest that as you increase scale down the supply voltage, dynamic power, that is measured data. Okay, they taken from one chip and calculate these things. If you scale down the supply voltage, dynamic power, definitely I mentioned, it is square law, it is going to reduce. But simultaneously your leakage power is also increased. And here it is going to dominate. Leakage power dominate. Your total power is going to reduce. Total energy is going to reduce per cycle. And then after it is going to increase. It means after this supply voltage, if you scale down the supply voltage, your total total energy consumed by the chip is going to increase. And the reason behind is that subthreshold leakage current. Other leakage you can control, but subthreshold leakage you cannot control because it's a MOSFET behavior. MOSFET behavior is like that. Cannot be below 60 millivolt decade. Okay, so we are searching or we are enthused in a new device that will overcome such issues. Come to next slide. Yeah, tunnel FET is one thing. Its conduction concept is the tunneling base. And the only difference between the tunnel FET and MOSFET is that the asymmetric doping we can place at the source side and drain side. Madam, time is there, no? Oh, number of things are there. Okay, please continue. Next slide.
Sub-threshold voltage depends on the designing of the MOSFET.
Yeah, it is the nature of the MOSFET.
Nature of the
We cannot change the nature.
It cannot depend on the material.
It cannot use the material. Actually, MOSFET is the conduction concept. Whatever the device, if we are using the thermal injection base, MOSFET means the current conduction concept is the thermal injection. Thermal injection means thermally it will induce. We are applying the voltage, does not matter. At least 60 millivolt is required to move. If you are going to apply less than 60 millivolt, current will not flow. Means your current will not change in order. That is the limitation with this one. It is a nature. Nature we cannot change. So we have to change the conduction phenomena. That is the number of devices there. Okay, I will make it fast. So you can go through these slides, and if any questions, I will give the answer. Okay, but it's a very interesting field also. Yeah, that is one important thing is that in a tunnel FET, it is more sensitive as compared to the MOSFET. The reason is that in subthreshold region, current is more as compared to the MOSFET in the same amount of gate voltage. In subthreshold, you know all you know, any device characters as subthreshold region, linear and saturation region. Okay, in subthreshold region, MOSFET, tunnel FET will have the more current as compared to the as compared to the MOSFET. Tunnel FET is the more current. It means its subthreshold swing is the reason is that subthreshold swing is less than 60 millivolt because it does not depend upon the such type of conduction. It depends only on the parameter like that you are telling. Here we can play with the parameters and we can go below the 60 millivolt. If it is there, it is more sensitive, and this type of a tunnel FET is useful for the biosensing application because it is more sensitive. Biosensing application means here you can see here we can put the cavity in gate oxide. That is the entire gate oxide. Gate oxide we can divide in a two part. One part we can keep it some dielectric. Other part we can put a blank, keep the cavity, and we check the performance. As we introduce any biomolecules, we'll have some dielectric. As we introduce, the sensitivity will change. And same thing we check with respect to the MOSFET. So MOSFET will not have the, although it will give the response, but it will have the good response as compared to the MOSFET. So tunnel FET is generally used for the instrumentation purpose, means sensing aspect. Got my point? No? So that's why I mentioned this one. That is the important thing. And someone have did the modeling also using the Poisson equation. And this one, you come to the next slide. These are the equations are there. So it's a very easy, although it is here you are observing and looking wise it is very difficult. But once you start, so it is very easy to understand because same thing will repeat. So same model they developed for this one. In this research paper, the person have introduced only cavity not for the biosensing aspect. They publish the paper in normal way in a good reported journals and transactions only. After they observe that sensitivity is good, why not we can rather than we can why not we can use the cavity for the biomolecules? Only they change the wording and they come up with the research paper with the biosensing applications. So that is the interesting thing here. Got it, na? So I suggest please do the modeling also. If you are interested, read this paper. I will share this one. I will share this reference. Go through this one and that will give the idea how we can go for the modeling. Yeah, now I come to this one. In 5 minutes I will conclude this one. Yeah, please come. Neuromorphic circuit, actually the main bottleneck of the our traditional computation is that our architecture, computation architecture is based on the von Neumann architecture. Means processor is one place and memory is at other place. Okay, so take the instruction and data from there, compute and again send it. That is, and it is a serial base and also serial communication, and it is synchronized communication. Okay, it is not a parallel computation. So neuromorphic circuit will come into the picture. It will mimic the hardware architecture and functionality of the brain in terms of circuit. But not only circuit, we have to use some neural network, that is coming the neuron. If neuron based means our brain will compute the things very speedily, and same brain computation, 1% of brain computation required the, as already someone did the practical on this one. 1% brain computation, if you realize using the traditional way, it takes number of processors, 64,000 processors of 1 GB will use for such computation. But now we can easily, and also it is not a real-time processing. We are doing all the things at real time. Our brain is computing all real time. I am observing to all, and my all sensing organs are active right now and will doing all process simultaneously real time. So this neuromorphic computation is useful for your robotics, and when we move toward this driverless car, or not, and we go for the send the our satellite where their such computation is required, real time computation is required, we go for this neuromorphic circuits. Okay, my two student along with my Finland friend, they are working for the specialized hardware. In the starting I said specialized hardware, not general purpose hardware. Specialized hardware means your neural network is there, that is made of the neuron. Over there some machine learning model will be there. And if machine learning model requires some mathematical computation, for that we develop some specialized hardware. It will not send the detailed data to the general purpose. It will dedicate for some specialized hardware. So we are developing we are going more towards the in-memory computation. When we, in starting, my students work on the Lineage 5 architecture, to understand the neural network, how it will work. Lineage 5 is the one architecture that is a CNN based. And we first we understand how it will compute with the TensorFlow, and then same we observe that in TensorFlow it is only vector multiplication, and then relies into the using the Python same layers we realize using all the layers we without TensorFlow. We write everything, all layers we write in Python again. Okay, and from there we can calculate neural network when it works. So we extract the all weights. Okay, I will come to them. Come next slide. Speedily, I will conclude. So this is the definition. It means neuromorphic circuit that will mimic the functionality of human brain, architecture and functionality. So you know very well why we are moving, because we want a low power, and our brain will like that only. Parallel computation and event trigger. If event will come for the vision, it will just only that neuron will activate. Rest of the neuron will not activate. But in traditional computation, continuously it will compute. So that's why power consumption is more there. Okay, yeah, come next slide. Yeah, here is the neuron. I think you already observed this one. So this is a neuron thing, and terminal action will come to this one. Yeah, neuron will actually such type of many more neurons are there, and we want to create artificial neuron so that we can use such for the computation aspect. So this artificial neuron, in general neuron, what will happen is the signal will come to the neuron, it will charge, and then which reach to threshold voltage, it will fire. Okay, fire means it will going to communicate the signal to the next neuron through the synapses. Synapses is there. Actually, in our neuron will have the, this is a neuron, and to communicate next neuron, there is a one interconnection, that is the synapses. Synapses elasticity will change in, that will memorize the things. If it is more elastic, it means more storing things are there. Okay, come to the next slide. Yeah, this is the artificial neuron. It is like that, whatever I said, information is coming, it is accumulate, and then using some function, it will perform the operation. Okay, so what you are observing in a generally 90% neural network algorithm work onto the vector multiplications only. And for your specialized hardware, if you are going to specialize hardware for such neural network, will work on the mathematics. Okay, so if any neural network needs some mathematical operation, so what will happen, rather than sending this mathematical operation to general purpose, will go to the specialized hardware and will perform the operation speedily. So in that manner, it will save the power. Yeah, this is a neural network, and this network will change depending upon at what context you are using. If it is sensoring, all sensor is changed, means if your retina is there, sensor, your ear, this sensory organ is going to change, this algorithm will change. But generally, hardware aspect, we can use the spike-based hardware neuron. Yeah, this is the same thing I mentioned. Yeah, so we observe this type of function, and we realize this function, this B is for the bias. Okay, and we realize we observe that the in multiplication and addition is required. And one more thing I am going to share here. We are moving in now the system is changing. System is changing from the digital domain to analog domain. That is, the new things are coming into the picture. If you perform the operation digital manner means if you want to perform multiplication and addition digitally through the processor, it will take time. 16-bit processor, 16-bit, 64-bit. But if you compute such multiplication or addition analog manner, it will take less time and it will save the power. And parallelly, you can compute all the things. So it will mimic your brain also. So that is the specialized hardware. Specialized hardware will change depending upon the situation. For what purpose for what biosensing operation you are going to perform. Accordingly, you can develop this along with your neural network. Once it will train, and your neural network will want to calculate some operation, so that task will be given to the hardware. Hardware will perform the operation again. Here CPU will work as the controller only. Specialized hardware will perform all the things. Yeah, that is the thing. That is the analog. These are some voltages that will come. Suppose some image is there. Image we convert into the voltage, and here we given to the voltage. And you have trained one neural. So once it is trained, it means we are going to fix the weight. Train means weight. Weights means synapses in a neuron. Synapses in neuron will be the weight in a artificial. So this is the weight. Once you fix the weight, whenever the neural network required, will get some inputs, will compute, will send the information. Computation is required, will send the information to the specialized hardware, and compute and will do this one. Rather than sending the information to the processor, will have the digital processor, will have the multiplication and addition will take more time. Here you can, yeah, please.
Sir, what about the accuracy?
Yeah, ma'am. That is the bigger issue. And currently we are working with this one with my group, with Finland friend. He is doing good in this aspect. We developed the Python model already. Actually, TensorFlow is there. TensorFlow, we convert whatever in Lineage 5 architecture. I think you heard about the Lineage 5. I don't know. It is some digital numbers. If you write the numbers, it will just detect and suggest that this is 9 or 8. This one. Okay. So it means this TensorFlow will have some weight. After training, forward propagation and back propagation, we do the training. Once it will train, it will have the weight. Same thing, madam, we have developed using all the layers we develop, write the same Python code without using the tensor library. We use all code, we have written all layers in a Python again. The reason behind is that because our purpose to go for the hardware, whatever the weights we use the DAC, because when we go for the hardware, we require the analog to digital converter and some in memory we have to place. So definitely your question is correct, ma'am. We are calculating the temperature non-linearity. We first do the all operation in with respect to hardware and checking the without changing the temperature, what is the computation, and the inferences come according to my VM architecture that is designed in a Python. It is equal or not. If it is equal, okay, then we change the temperature. What is happening? And same non-linearity we can calculate. We calculate and we integrate into our VM model so that it will become the more accurate. Like non-linearity is the biggest challenge in such type of analog domain. So most of the research papers they are working only for the non-linearity aspect. Got it, ma'am? You are getting my questions? Actually, non-linearity itself is the issue.
That's why
Yeah. So here, just give the picture here. System without AI accelerator. Actually, this is the AI accelerator. AI is the very big task. And what are the hardware we are using? Depending upon to the algorithm, respectively, especially hardware, we can use it. Okay. So without AI accelerator, CPU will divide the work between the GPU or TPU like that. It will divide and will perform the operation. Okay. Come to the next slide. If you place the AI accelerator, so CPU will give, once get the CPU will the signal, I want to perform such image processing, will give, specialized hardware will be there, it will allot this work to the hardware and compute it. And CPU will be free and it will be the it consume less amount of power. Okay. So this is the thing. Please come to the next slide. Yeah, this is this architecture we are working, Linet 5. Because I am also new here for the machine learning on this aspect, and as per my experience, we need to learn the Python, we need to learn the data science, we need to learn the machine learning also. It is very difficult to accommodate continue our research without this aspect. Okay, because terminology is changing, and with respect to such a learning model, we are working all these aspects. Even you are working for the device, you have to learn the all machine learning or such new type of a domain. Okay, so we are working for this Linet 5 to learn the all machine learning aspect and CNN arcade neuron based. Number of layers are there. I don't want to go in deep. Okay, already we are going away from the time limit. Yeah, please. Yeah, okay. Please come to the conclusion slide, ma'am. Madam, please share this slide if they are interested. Okay, so yeah, please come to the last slide. Yeah, some sensory networks I want to discuss. Okay, I will discuss later on. Yeah, this smart watch also. Here you can see here. This smart watch will have these two sensors, biosensors, heart sensors, and this one. So AI means it will not measure only suppose it is sensing the blood oxygens. It is not only, it will not show the definitely show the 98%. But what are the other things are connected with this blood oxygens? So such data is there. We trained the model. We trained our model. If with the help of this only single parameter, how many diseases you can predict? At that time, we can go for the AI accelerator. Otherwise, what is the use of AI? So totally, the domain is shifting towards the data point of view. So it will give ultimately AI means it will predict what is happening, what is the possibility of one particular disease. So that is the meaning of the AI only. And accelerator means if any AI neural network, if it is neuron-based neural network, if it requires some computation, you have to place some hardware for that, specialized hardware that dedicate for only for that purpose. So it will save your power and it will be good, helpful for the your advanced smart devices. Yeah, same thing it is mentioned here. So these are the advantages I already mentioned. So here this is the main conclusion point. I discussed this thing. Gate around nanosheet is the right candidate for the MOSFET aspect, for the biosensing and circuit applications. Now the industries are moving for the 3 nanometer, only they are using this nanosheet. And its alternatives are there, they will move for the 2 nanometer also. And second one thing, I mentioned the tunnel FET is the promising device that is alternative of the MOSFET. Other memory elements like the phase change memories also I want to cover, but that is also alternative for this memory aspects. That is a device aspect. Okay. And neuromorphic circuit is the future of the computation. Okay, so if you have any questions related to this presentation, I will share you. Okay, if any questions, you can talk me right now, or anytime you can put the mail or call me, I will give the answer.
Sir, as you mentioned in your presentation,
Huh?
you have mentioned one parameter that is lambda.
Lambda.
You have mentioned that it should be as low as possible.
Yeah, correct.
Then for that, you have mentioned that we move from normal FET to fin FET. Then after that, you have introduced another FET. But what was the drawback which was there with FinFET? That is, you introduced 4 gates, and after that, you have introduced some other FET. So what was the drawback due to which you switched to some other FET?
Means you are telling that lambda is the parameter I use. Actually, lambda is the one parameter that measure the how much drain electric field encountered towards the source side. Okay, that is the lambda. It is applicable for all type of transistors. Okay, through this parameter we can understand whether my dibble is in under control range or not. Okay, once it is confirmed, then we can go for this one. And the drawback for the upper device means higher node, only the capacitance is the big issue. But the capacitance, because our around side we can put the gate oxide. Capacitance definitely performance in terms of delay will increase. But the another advantage is we are scaled down the transistor. So source and drain will come very close. So the speed will enhance. Getting my point, na? So some trade-off is there. Means we have to capacitance, somewhere we have the capacitance, but sometime we also increase the current also, and also improving the gate controllability. Got it, na? Sir, any questions?
Yeah. Actually, you all discussed there are so many issues related to short channel effects.
Yeah, correct, sir.
But you shown one slide in which there is a long channel also there.
Yeah, correct.
So why not you discuss more on long channels? What is the drawback?
Actually, long channel, why I mention here, that is the only baseline, sir. If you go for the long channel, how we can distinguish between the long channel and short channel? Micrometer, I can also say the short channel with respect to millimeter. Okay, the reason is that that is the standard definition for the short channel, as the researcher have quoted. If the channel length is comparable with the source and drain depletion barrier, in that case, channel length, this device is called the short channel. And if you work for the short channel with respect to long channel, because we have to develop the model, mathematical model, because ultimately goal to develop the model, that model is useful for the circuit design. But if you use the long channel device model for the circuit design for the 14 nanometer node, it is not correct, because number of non-linearity we have to include in our model, so that our model become more accurate. Okay, na sir? Getting my point, sir? So that's why I introduced the long channel. Those who are working for the device modeling, developing the mathematical compact model, so they start the working for the, first they understand how the current is flowing and how we convert into the mathematical equation. Then after we can introduce different type of a non-linearity and make our model more accurate. That's why I mentioned this one.
Sir, in your definition, that you are telling that the in short channel, the gate will be compared to the depletion layer. So how much comparable? That means 50%, 70%?
No, comparable means if it is going to equal. Suppose channel length is 45, channel is 45 nanometer, okay, and depletion width at the drain side is more. If it is around like that 35 nanometer like that, so it is a comparable, okay. So it means some, yes, like that we can do it. And some reason it is going to more than channel length, and because another short channel field will become, punch through will be there. When both the barrier will touch to each other, electron will pass very high speed. So we have to avoid this punch through, but somewhere it is advantageable. For I am discussing here for the biosensing application point of view and circuit aspect.
So in punch through, I think the device behavior is linear after that.
It will no, electron will pass very high speed and might be the linear, sir. Okay, ma'am. Thank you very much.